Good morning, everyone. Welcome to the another lecture of atomic structure. Myself, Suman Singh. So, in the last class, we were discussing about the line spectrum of emission spectrum of hydrogen, right? So, this was this graph this diagram we were discussing. So, we will start with the very first. So, suppose what we will do here to understand this, we will take one container, okay? We will take one container here, and in this container we will put hydrogen gas. Okay, hydrogen gas. Now after putting hydrogen gas in this container, what we will do, we will pass energy to this container. Okay, we will pass energy to this container. So what will happen at that time, the atoms of the hydrogen which is present in this container will take energy, and it will take energy from the source which we are applying here. It will take energy and it will go into the excited state. Means previously, when these energy sources of energy was not there, at that time whatever the gases of hydrogen or the atoms of hydrogen which is present in this container were suppose at the ground state. Okay, gs, ground state. Now after passing sources of energy, what they have done, they have consumed the energy, and after consuming the energy they have reached to the excited state. Okay, suppose this thing you have to remember. After that we will discuss about this. So this, in this diagram you can see that this line, whatever the line it is there, right, 1 2 3 4 5 6, like this line is what, different energy state. Okay, different energy state. So suppose this one, the first line, this line we will consider this line as ground state. Okay, ground state. And this one is our first excited state, second excited state, third excited state, fourth excited state, fifth, sixth, seventh, up to infinity, right? So suppose when we have supplied energy to the hydrogen which is present in that container, so what they have done, they have consumed energy, and by taking the energy, suppose some of them suppose they have some of them has reached to this first excited state, or suppose some of have them has reached to second excited state, some of them has reached to third, like this, fourth, some of them is fifth, sixth, like this. Okay, after taking the energy from that sources. So now some will get, if some of them will get if very high energy, then it may reach to infinity. Okay, like this. So so what we are seeing here, that after taking the energy, electrons or atoms of hydrogen is shifting to different energy levels, right? Now after some time what will happen, after some time they will release their energy. Okay, so when they release their energy, at that time, suppose any of the atom from the, it is if at the time of releasing the energy, if it is if it is, suppose he was at that time he was in this seventh energy state. Okay, seventh excited state. So what they have done, what he has done, he has just, that atom has just released their energy. So after releasing the energy, if he jumps to the first ground state directly, you can see here, no, ground state. And suppose some of the atom was in some of the atom was in sixth excited state. So he also jumped from there, he has jumped to first excited state. So in the same way, if some atom was there in the fifth excited state, he also jumped from there into the first excited state. In this way you can see here, from the fourth also, from the third also, and from the two also. Means what we can say, that if suppose some of the atom was there in infinity, from the infinity also, if it is jumping to the first energy state. Okay, so at the time of when they are jumping from the sixth, seventh, eighth, or infinity to first ground state, you can say this is ground state, right? I have told you about ground state. So if they are jumping to this region, means this region. After releasing the energy, the atoms are jumping from their excited state to the first here in this state, means the ground state, or you can say that ground state. So that type of the series, the band will generate whatever the band or the series which will generate there at the time of jumping, or the energy which they will release at the time of jumping, that type of series is called, this series is called Lyman series. Okay. Now again, if some of the atom is jumping from 3 to this first excited state, or 4 to this first, or to 5th to this, or from 6th, or from 7th, or from 8, like this. Okay. So this reason, when they are jumping from here to here like this in the first excited state, this region is called ultraviolet region. Okay. So whatever the radiation will come out, that will be in the ultraviolet region, which is not visible with our eyes, as we know that, right? Now if it is jumping from jumping to the first excited state. Okay. First excited state, this is suppose second excited state, third, fourth, and fifth. So if it is jumping from infinity, or from 8, or from 7, or from 6 to 1, like this here 1 in the in the ground state, then that type of series, we have series that will generate, that series is called Lyman series. Now again, if it is jumping to the second first excited state, then it is called what, Balmer series. You can see here it is written Balmer series. So Balmer series is what, it is a visible region where we the Balmer series, whatever the light will fall on the Balmer series, Balmer region, that will be visible to our eyes. Now in the same way, if some of the atom was in the infinity, and from that it has jumped to this place. Okay. In the second excited state, jump to this place, suppose. Okay. So this is called what, Pascal series. Okay. This Pascal series is you can say that this Pascal series region is an ultraviolet region. Okay. Yeah, sorry, infrared region. Infrared region. Okay. Which is again not visible with our eyes. And now suppose if it is jumping to the, this is what, fifth excited state, right? If it is jumping to the fifth excited state, means it is what, Bakelite series. Okay. This is what, Bakelite series. Now if it is jumping to the you can see here sixth, then it is called Buffon series. Okay. I hope you have understood this, what is the meaning of this Lyman series, Pascal series, Balmer series, and Buffon series. I hope you have understood this. Now this always remember that this the diagram which I have shown here, it is it's only for hydrogen. Okay. Not for any other element. So this was all about the spectrum of hydrogen, or we can say that the hydrogen emission spectrum. So you can see that you can easily calculate the energy of this reason, just like the Lyman series. What we have seen, you will be given one formula. You can see that the wave nature for any single electron species. Single electron means what? Single electron system means what? Hydrogen is what? Hydrogen, you all know that atomic number is 1, and that is why its number of proton is also 1, and number of electron is also 1. Okay. So one electron system means what they have written, single electron species. Single electron species means what they have written, you see here, He plus. He plus means what? Helium is what? Helium has the atomic number of 2, right? Means 2 electron and 2 proton, 2 electron and 2 proton. But H plus is there. If we are writing H plus, means there is one only one electron but 2 proton. So those species, or those element, or those element in which there is only one electron, that is called single electron species. Okay. Just like He plus and lithium 2 plus, just like this. Okay. So for single electron species, and we can calculate one equation. You can see here, wave number, it is right, V bar, what we call now wave number. So we can calculate the wave number easily. So how we can calculate? This is Z is what here? Z is the mass number. Okay. Z is what? Z, you will see here, it is everything is written in detail here. So Z is what? Z is here Z is what? Mass number. And that RH you see here, na, RH, that is called Rydberg constant. Okay. Rydberg Rydberg constant, which we will learn afterward about this. And this n1 and n2 is what? Suppose we will understood about this one n1 and n2. You can see here what I have told you. This is now z is what? This is mass number. This is Rydberg constant. And n1 and n2 we will see what is n1 and n2. So n1 is what? In a Lyman series, what I have told you, it will jump to the first energy level. Okay, so and from where it will jump? It will either jump from 2, or you can see it will jump from 3, or we can see it 4 5 like this. Now you can see here Lyman this one, this series we will take as n1. Okay, and from where it is jumping, you can n2. The from where it will be it will jump, that will be n2. Suppose it is jumping from this place, or suppose this place, or this place, or this place, anywhere from where, and from where it is jumping, that will be n2. Okay, so you can see here, and in the Lyman series, n1 is what? N1 is 1, and n2 will be anything, 2 3 4 5 6 7 up to infinity. In the same way, Balmer series, when we talk about the Balmer series, you can see n1 will be 2 and n2 will be from 3 to infinity. In the same way, Pascal series, n1 will be 3 and n2 will be 4 to infinity. After that Bakelite series, you can see n1 is 4, and after that from 5 to infinity, that will be n2. And the Puffin series, n1 will be 5 and n2 will be from 6 to all the integers. Okay, so in this way you can find out the value of this wave number from here, from this equation. Okay, so I hope all of you have understood this. Now after this we will see what? Bohr atomic model. Okay, so I hope all of you have got some idea about the spectrum, and the hydrogen spectrum, and in the previous lecture also I have discussed about this different type of spectrum and all, right? And now we will see Bohr model of atom. So Bohr model of before discussing the Bohr's model of atom, so always remember that Bohr has given his model for only single electron system. Okay, just like in the case of hydrogen atom, he has not calculated, or he has not given his model on multi-electron systems spaces. For multi-electron spaces, they have not given. He has not given his model. He has given his model only for a single electron spaces, because if there is a single electron, so if suppose we are talking about the hydrogen, so this is suppose proton and one electron is here, so we can easily, we can easily calculate, because the energy we will consider here, only one or two type of energy we will consider here. Okay, and if we are taking the multi electron system, then you can see here, from these two electron will also repel each other, this will attract each other, and so many other thing will generate. That is why Bohr, what he has done, he has given his model only for a single electron spaces. Okay, so before that we have understood that from the Planck quantum theory and classical physics has just explained that light possess both particle nature as well as wave nature. Okay, as we have seen in the Planck's quantum theory, we have seen that the light is just the small packet. Light comes in a small packet, which is called quantum, and in the classical physics they have explained that the light is a wave. So from that we have got the idea that light has both the nature, particle as well as wave nature. Okay, so we can get, I will give you one example also, that the light has both particle and wave nature, just like this. If there, if we are considering a wave as a particle, okay, if we are considering a wave as a particle, then what will happen if suppose the, if we are considering what, wave as a particle, then suppose this is a source here, and from this source light is coming like this. Okay, light is coming like this, light is coming like this. So if it is a particle nature, and if we put one matter here, what we will see, that the matter which is here, the particles which is here, if it is barrier, suppose we are using a barrier here, then the particle will not cross this, and this will be look like this, okay, because if we are placing one barrier here, then the particle is not passing, right? Now if you are considering light as a wave, and suppose this is a source of light, then it will generate like this, wave will generate like this light. And if we are putting a barrier here, what we will do, what wave will just do like this, right? So in this way, barrier, if we are placing a barrier, and if we are considering light as a wave, then you can see the changes here. But if we are considering light as a particle, then you can see the changes in this two picture, right? So in this way, we have got the idea that the light possesses both particle as well as a wave nature. So now what Bohr has told about his model, we will see that he says that the electrons revolve around the nucleus, okay, with a definite velocity in a certain fixed closed circular path called orbit, okay. Orbit, or we can say that the stationary state. This cell and the orbit is numbered as 1 2 3 and 4, less like this, K L M N O, you can see here in this diagram. What he says, the electron revolve around the nucleus in a specific permitted circular orbit and in no other orbit, right? So you can see here, each orbit has given one, n is equal to 1, n is equal to 2, and n is equal to 3. But as you remember that in the Rutherford model, what he says that the electron revolve around the nucleus, um, but he has not told that the electron is revolving in a fixed orbit, okay. He just said that the electron is revolving around the nucleus. If any charged particle is revolving around the nucleus, then you will learn that according to the Maxwell theory. So any charged particle is rotating any other charged particle, then one time will come, this electron, the charged particle will lose their energy and it will fall into the proton, okay, if we are considering electron. So in the same way, what Bohr has told, that the electron revolve around the nucleus with a definite velocity, means the velocity of the electron will be fixed, okay. Now the in a closed circular path, which is called orbit or cell, okay. And that cell he given the name as 1 2 3 and 4. Now number two, what he says, that each orbit is associated with a definite amount of energy, means whatever the orbit we are seeing here, n is equal to 1 2 3 like this, they will have a definite amount of energy, means their energy will be fixed, okay. As long as the electron is revolving in an orbit, it neither loses or nor gain energy, and hence the orbit are called stationary state or stable orbit. What he means to say, that each orbit, whatever the orbit in which the electrons is revolving, the energy of that orbit will be fixed, okay. And at the time of rotating, when the electron will revolve around the nucleus, he will neither lose energy or nor he will gain energy, okay, in the stationary state, okay. In the stationary state, it will neither lose energy nor it will absorb energy, and that state is called, that orbits are also called stationary or state, or the stationary orbit. Now next, what he says, that the centrifugal force of the revolving electron in the stationary orbit is balanced by the electrostatic attraction between the electron and the nucleus. You can see here from this you can easily find out. So when the electron is revolving around this nucleus, around this is a nucleus, right? When the electron is revolving like this, so at the time of revolving, it will generate what? Centrifugal force. So that centrifugal force, what it will do, it will make the electron to come like this, okay, this way. But due to the electrostatic force, what it will do, which is present between the nucleus and the electron, so it will repel that one. That is why both are balancing each other. That is why electrons are just revolving in a fixed orbit, okay. I hope you are understanding this. And about the electrostatic force, and this electrostatic chapter is there in class 12, the first chapter of physics. that is electrostatic is there. So you will learn about in there about the electrostatic in detail in class 12. Okay, so now so what he says that the centrifugal force of the revolving electron in the stationary orbit is just balanced by the electrostatic attraction between the electron and the nucleus. Okay, now again what he says, angular momentum. I hope you all of you have learned in class 10 or 9 about angular momentum, which is mvr, right? mvr. Okay, what he says that the angular momentum of the angular the electron which will revolve in the around the nucleus. Okay, the electron, that electron can revolve only in the orbit whose angular momentum are an integral multiple of h by 2 pi. Okay, if the angular momentum of the electron of that orbit is h by 2 pi, then only the electron will revolve there. Okay, you can say like this, that electron can revolve only in orbit whose angular momentum is an integral multiple of h by 2 pi. So for first orbit we can easily calculate, right? For first orbit it will be what? It will be actually it is mvr is equal to h by 2 pi, it is nh by 2 pi. Okay, n is what? Number of orbit. Suppose for first orbit what we can write, for first orbit n is equal to 1, right? So n is equal to 1 means h by 2 pi. For first orbit angular momentum will be what? H by 2 pi. And for again for second orbit, here we will write n is equal to 2, then 2, this 2 2 will be cancelled out, it will be what? H by pi. Okay, now in the same way if we are taking n is equal to 3, then it will be 3 by 2, 3 by 2 h by pi, like this. If we are taking 4, then it will be if we are taking here 4, then 2 and 2 4, it will be 2h by pi. So like this way we can easily calculate the angular momentum of the orbit. So for a first orbit h by 2 pi, for second h by 2 pi, for second orbit h by pi, and for the third orbit it will be 3 by 2 h 3h by 2 pi, and after that fourth orbit 2h by pi. So like this way we can easily calculate the angular momentum of the orbit. Now next, and here when we are talking about mvr, m is what? Mass of the electron, and v is what? Velocity of the electron, r is what? The radius of the orbit, and the n is what? N is an integral number like 1 2 3 and 4, which is also called the principal quantum number or Planck constant. We will learn about this Planck principal quantum number, and what quantum number is what, we will learn about this in detail. Okay, so radius, if you are calculating the radius is what? You can see here the distance between this one and this one, this distance is called radius, or we can get this is the radius, or this is the radius. Okay, so this was about this. Now next, what he says, the energy of an electron changes only when it moves from one orbit to another. Okay, outer orbit has higher energy while the inner orbit has lower energy. Now, and one more thing, the energy is absorbed when an electron moves from inner orbit to outer orbit, and the energy is emitted when electron jump from outer orbit to inner orbit. Let me tell you what he wants to say. We will see here. Now, the energy of the electron changes only when it moves from one orbit to another. What he wants to say, suppose this is a nucleus here, and this is the first orbit, second, third, like this. Okay, so what the Bohr has said, that the energy of the electron changes only when it moves from one orbit to another. Means what? If the electron is revolving in this orbit, suppose, okay, so when it will jump here, okay, when he will jump here, at that time only the energy will release or absorb. Either energy will release or absorb, and when energy will be released and when energy will be absorbed, we will see that. Okay, so energy changes, just remember like this, if energy is changing, means the electron is either jumping to the higher energy level like this, from 1 to 2, or from 1 to 3 like this, or it is just jumping from 1 to 2 or 3 to 1. I hope you are understanding this. Means what? When there will be a change in energy of the electron, energy of the electron will be seen when the electron will either jump from, suppose this is the first energy state, this is second, and this is third, right? So if the electron is jumping from 1 to 2, or it is jumping from 1 to 3, at that time energy will change. Or if it is the reverse, if we are doing the reverse, if it is jumping from 3 to 2, or if it is jumping from 3 to 1, at that time also energy will change. Now, when energy will absorb, when it will jump from lower orbit to higher orbit, when the electron will jump from lower orbit to higher orbit, from means from 1 to 2, or from 2 to 3, or from 1 to 3, when it will jump like this, at that time energy will be absorbed. Okay, when it is jumping from 1 to 2, or 1 to 3, or from 1 to 4, or from 2 to 4, like this, when it is jumping to a higher orbit, at that time the energy will absorb. Okay, now you just make opposite of that. If it is jumping from 2 to 1, or 3 to 1, or 4 to 1, or 4 to 2, or 4 to 3, at that time the energy will be emitted. Okay, the energy will be released. I hope all of you have understood this. Now next, what he says that the energy emitted or absorbed is transmitted, the energy emitted or absorbed in a transition, when he was changing from 1 to 2, or 2 to 3, or just like 2 to 1, like this, at the time of transition, will be equal to the difference between the energy of the two orbit. Okay, suppose the energy of the second orbit is E2, and the energy of the first orbit is 1. So overall absorbed or emitted energy, which we, if suppose we are taking as delta E. Okay, so it will be what? E2 minus E1, and which will be equal to h mu. Okay, I hope you have understood this. So this was about the Bohr model of atom. So from the always remember that in the starting also I have told you, Bohr model is just for a single electron system, just like hydrogen, He plus and lithium 2 plus, like this. Okay, not for a multi electron system. So now next we will see expression for the radius of orbit. Means what? Radius of Bohr orbit. We say that the radius of Bohr orbit. So how to calculate the radius of Bohr orbit? There will be a simple process, very simple equation is there. Just you need to practice this. Okay, because in the exam sometimes they used to ask directly the expression, calculate the radius of the Bohr orbit, like this way. So you have to know this. So how we will see? You can see here this one. Okay, you see this one. This is the nucleus. Okay, in this nucleus, suppose there is a charge of okay, we will see this in the next class. Okay, because it will take some more time. Okay, so we will see this in the next class. Okay, I hope up to this Bohr model of atom you have understood. So we will see in the next class about the calculation of Bohr radius and calculation of velocity, and after that we will calculate the energy of the electron. Okay, these three things we will see in the next class. So keep up to this. Thank you.